Hello, hello.
So one quick announcement. Those who are having trouble getting on the EduRoam, I have a guest username password to use the Wi-Fi. So it's on there.
Okay.
Oh,
Oh,
yeah.
Hand this to this speaker.
You got the mic, so.
This is for you.
We get to ask questions of the speakers.
You can start it off.
I'd like to know in terms of the coastal ocean CO2 flux, how do you think the extreme events alter the present global models for that?
Bob, that's a hard question. As far as we have seen from all the data we have collected, it's definitely transferring the carbon from the sediment into the atmosphere in a short term. It's longer term effect. I haven't come across any paper which have actually modeled in, but we do have a collaborator in our project with NASA who's trying to collaborate that. Actually, there might be a poster. Shachang, are you having a poster on that? Oh, no, not just the global one, but not the episodic events yet. But I think it should be an important component because if you think of it, the Mississippi sediments have only 0.5% organic matter, but it gets a lot more. Where is it going?
So that's always been my my problem with a lot of the global flux models is that it's inconsistent with the storage of carbon patterns.
Yeah.
I mean, they show the coastal ocean being a big sink of atmospheric CO2. And yet when you look in the sediments, all the carbon that's coming in, a large proportion of it's lost. So somebody's got to be wrong.
Yeah. Yeah, no, I agree. Totally.
And maybe the way out is some of the sort of the aliases between when people make measurements of fluxes and when it actually occurs. And if you have these extreme events where nobody is around, maybe that's one of the reasons. Does this work, or is this just a placebo, Mike?
So we have the nice diagram about looking at different time scales and spatial scales. And I think to get at these kind of long-term, what stays in the record questions, then we go from the monitoring and instrumental work that's short time scale. We have to go back to the longer time scale reconstructions to look at what's preserved in the sediments on the ocean floor and the delta layers.
Okay, following on to that conversation about when this remineralization happens, do you have a sense for what, I guess, pools of carbon are being remineralized? And thus, is there a pool that's being preferentially preserved in the sediment after these events?
Did everyone hear that?
Okay, so do you have a sense for what pool of organic carbon is being remineralized preferentially versus being preserved in the sediments during these events?
Well,
Well, I don't know about what's injected into the water column, but in the sediments, you invariably see a fraction, what I call diagenetic fractionation of isotopic compositions, as opposed to mass-based fractionation of isotopic compositions. So you generally see a buildup in pore water of relatively heavy CO2, del C13 CO2, which is telling you that marine carbon is a lot of the support for what's remineralized. And you also see that it's younger. Carbon-14 tends to be relatively young, but there's still a component of what you might infer to be more refractory carbon in the CO2. So it's quite possible that these events that remobilize and re-expose organic material actually result in a greater introduction of some of that more refractory component. So what I'm saying is that I don't know. But it's probably a little of both the older pools that have a terrestrial type carbon-13 signal and and an older carbon-14 signal, but also a large proportion of the same thing that's being seen in the seabed would be my guess. I don't know if that answers that. That'd be my guess anyway.
I agree. I think it's also, if we look at at least for the shelf, Mississippi shelf, it has a more dominant terrestrial signature in the carbon, but it has a lot of high productivity, marine productivity going on. Where does it go? So that's the first part that is obviously getting remineralized, but these events may actually introduce these more recalcitrant forms that gets respired again.
At least in the silicons. So the biogenic silica for a diatom is coated in organic matter because the silica is undersaturated everywhere in the ocean. So when you see that silica dissolution, that organic matter has to be stripped at some point. So when we see after the storm events, you double the pore water silicon, you've introduced a significant amount of that diatom silica, which means that the organic matter was protecting it is gone. And given the isotopic composition of that material, it's likely marine and water column. So that's probably, that's definitely not an older pool, but it is a labile, or likely labile. So why, I don't know, but how important that is, but it is a component that we can see.
Thank you all so much for all of your presentations today. I really appreciated everything that you shared in your respective studies. Those were all very specific, and I want to go back to one of the questions that we had in the opening. From what all of you know about deltas around the world, which one do you feel, those of you who do want to speak to it, is in the most danger at this point in time?
By danger, do you mean extensive modification of what you would expect naturally, or a complete loss of the delta system? I mean, there are some areas that used to get tremendous sediment input, like the Yellow River, that is essentially gone. I mean, that has zero input. And the Colorado River is another river that used to be ranked highly in terms of the amount of water and sediment it brought to the ocean. It brings nothing now. It's all used by human beings or trapped behind dams. So I think you can go across the planet and see where people have built the biggest dams and taken out the largest amounts of water for irrigation and so forth. And those are the deltas that are either going to be eliminated or drastically altered. But I think actually perhaps another speaker later on in our workshop, Yap, will speak to this, because he's done a lot of these kinds of estimations of changes. But yeah.
Also, if you think of population, Ganges Brahmaputra Delta has half the population of US on it. So that's a huge human impact right there, any changes.
One interesting thing to contemplate locally is, it's thought that even with the investment of billions of dollars in coastal protection, in 50 years, the Mississippi River Delta may disappear. So what does that mean in terms of the coastal ecosystem, hypoxia, fisheries? On the one hand, you're potentially making the circulation along the coast a little more open, and so maybe you can get more water through. On the other hand, right now, a fair amount of the nutrient-laden Mississippi River water comes out to the end of the delta, past the shelf break, the delta goes away and now it's coming in shallow water. So maybe that exacerbates the problem. And I don't think anybody knows the answer to that.
Hi all. Hello. Thank you for all the informations. Hello. Can you all hear me? Okay. Great talks. And I'm particularly more interested in the fluid mud that was mentioned in one of the talks. And from a physics perspective, I feel like a background. I feel like I'm getting brainwashed by all the chemicals in the talks. So my question is, the fluid mud, are they consist of a selective group of materials? I imagine they're lighter. And if yes, are they protective of reactions or chemical processes at the actual solid bottom? If not, they're homogenized and they are the same with the bottom sediment, more solid sediment. Are they not protective to them? If that makes sense.
I guess that's something I didn't have time to show you. Is that in fact these muds they recycle iron oxide, which is what you talk about earlier in Bob's talk on the Amazon. We see the same thing in the Mississippi. The iron is recycled, so it's regenerating on a good electron acceptor to oxidize more carbon. Trying to explain to a physicist how it works, right? And we don't see that with manganese because the kinetics of manganese cycling is different. So we see manganese fluxing out of the sediment and then transported later on the slope or actually along the shelf. In terms of carbon, the protection of carbon, that's a different story. I'm not sure if you can add on to that. I mean, it's very difficult to be able to measure that.
There is some size fractionation from if you have a seabed that's got a particular distribution of particle sizes. When it's disturbed and mixed, there tends to be a bias toward the finer material being retained in suspension. And these fluid muds are generally 10 grams of solid per liter of water or more. So and they behave like fluid. I mean, they like heavy fluid, and sometimes they look when you drop a instrument like a conductivity meter into them, and you think you're measuring the salinity of the water, and you'll see it drop. So it looks like in these fluid muds, like the water in them is fresh, but it's not. It's the conductivity of the fluid has been lowered by the massive amount of solid that is suspended in it. So I would say to people who make measurements with CTDs that be aware of the fact that if you're in a fluid mud layer, you're probably not getting an accurate salinity measurement. So this is all part of the properties of these things. And in terms of the remineralization properties, I don't think we know very much about it. They tend to be reactive. They tend to produce a lot of CO2, but exactly how that goes back to the amount of carbon that's lost from the fluid mud, I don't know of a study of that myself.
I had a question. I think for all of you, you talked about timescales a lot and about things that change, hurricanes, seasons. So in your assessment, when you think about the fluxes, what has a bigger effect? Is it the hurricane or is it the seasons?
I'll take this. We had this challenge with our data set because those first couple months after the hurricane, it's like, okay, so we've seen this enhancement of dissolution and the buildup in pore water, but we don't know what a normal season looks like. And then, at least for silicon, as it was being consumed, it never necessarily got back down to that initial condition. It felt like this single event had this kind of disproportional effect over what we were seeing in the natural seasonality. Now that's for one element. And so, I'd be curious on what other people's perspectives are for carbon and for other elements.
I think it will also depend on the water depth we're talking about. I think that is the biggest determinant in some sense. The shallower the water, the bigger the impact of these hurricanes in this system. So maybe in a delta with a different morphology like Congo Delta, which is much steeper, maybe hurricane is not that important. But in Mississippi Delta, where it is short, a really 40, 50-meter water depth, I think it is very important comparative.
But I think the effect of seasons also, when you think about tidal fluctuations, for example, or seasonal fluctuations, you think they're very important at 50 meters?
Probably not. No. Yeah, I think the hurricane is kind of like it's going to redistribute it more than any seasonal changes will happen.
That's kind of what I meant when I was speaking earlier, that the forcing factors in the different regions can be really variable. And so the tides are obviously the daily tides and that kind of, and seasonality and flow can be definitely dominate the fluxes in particular areas. But you get into the deeper regions that aren't normally affected by that, and an episodic storm can remobilize material and move it offshore or inshore. And so I'm not sure there's a single answer to your question, actually.
Yeah, I would add on that we saw similar things, like I was talking about that July 21 time period where the discharge was so high on the shelf. We measure benthic flux that were basically varying over time in the chambers. And so these effects definitely, influence the fluxes, and other time then you don't see that. So this huge variability that's very difficult to take into account.
I actually have a question about biogenic silica and the ingrowth of dissolved silica that you see, because in the systems that I've worked in most commonly, the silica after a disturbance is depressed in the dissolved concentration, and it takes months to grow back in. Well, maybe weeks, I would say, based on incubations of the sediment, but you're seeing an almost instant response to ingrowth. And so I'm wondering, is that due to the much higher basic biogenic silica in Mississippi Delta sediments? How does the Mississippi Delta biogenic silica in the surface sediments compare to other deltaic sediments? I guess that's my real question.
So compared to like the Amazon, they're actually fairly comparable. I think, like in most systems, the sediments here are ultra low for biogenic silica. So, typically 1%. And so that would be similar to what you see in the Amazon, but they're definitely not like, oozes that you have in the Southern Ocean or the Bering or even most kind of coastal shelf sediments. One of the things that I think happened in this station was we're trying to figure out why things changed the way they did. And one of the kind of things that we've talked about a little bit is that because the significant wave height was so exceptional, up to 15 meters at a 45-meter site, you actually had changes in hydrostatic pressure that could have basically been doing things to the sediment water interface that you might not normally see, because we have evidence that there was oxygenation pretty deep, but we don't really change the grain size significantly from the beginning to the end of this or post-storm. But we have evidence that you had this kind of pulse of oxygen or some sort of a shuttle that went pretty deep. And so if that's the case, then if you oxidized, then you can stimulate microbial activity to start stripping that organic matter off the diatoms to liberate the silica and help it build up in the pore water. And then, maybe once the suboxic conditions re-establish, you can start drawing it back down.
Thank you. Excellent talk. I really enjoyed the effect of hurricane and water content structure, how it impact the deltas and Mississippi Sound. Actually, Mississippi Sound is my star area. I'd like to hear some insight how submarine discharge impact biogeochemistry of Mississippi Sound? Could you please share?
Well, I wish I had the complete answer to that. But what we think right now is at times of the year when river influence is low, the SGD delivery of nutrients becomes a major factor. When the local rivers are high, maybe the rivers are more important, but SGD is still significant. And then when the Bonnie Carey spillway is open, and so you've got nutrient-laden Mississippi River water coming in, then the SGD impact is minimal.
Yeah, thank you. I also have a bit of a broader question relating to what Jaap said. You have shown a lot of work now a little bit on the outer, deeper waters. I study mainly the marshes. So I wonder, is there evidence how these processes affect delivery to the marshes? You were mentioning the change in pH, for example. Does this like get inland? Do we know anything about how these processes affect like the marsh?
On that, actually is working across the back of the bay, which is a big issue. There are changes, especially microbial changes that are happening. So microbial changes that are happening and new sedimentation rate, thick layers of sediments that are getting deposited, we can easily see that marked when we collect a core. So that gives us a really good chronology of what is happening above it. So I would expect big changes in the marsh, in these marshes too, especially in the estuaries inland, especially the salinity is going to go up with all the storm surge and the sediment delivery. So, but we haven't really looked at the data yet.
Hi. Thank you for the very nice talks. It was very interesting and also exciting for the coming discussions. I just wanted to make a comment on some things, because when I looked at Bob's presentation, I see that sometimes in different settings, different deltas, you can interpret things differently. Like we, delta have very large sedimentation rates, we believe. And so very flat lead to 10 profiles, as Bob showed for the Amazon, but it's a very different hydrodynamic setting and also movement of sediment. And so we end up with, you can see that on the poster I have outside, we end up with a decoupling of oxygen on DIC fluxes, which can be attributed to non-steady state, but in our case, we think that it's reduced products like iron and sulfide that can be buried very efficiently because of the high sedimentation rate. So all goes in circles. And then creating this decoupling between DIC and oxygen, and also between DIC and alkalinity at the same time, because you sort of somehow bury some negative alkalinity, let's say, so it promotes alkalinity. Or you can come on check on the poster. So I think the interpretation we have of observations can also vary between different settings. And that's one thing that during this workshop we should try. I think we should try to keep discussing, but also I think it would help us by contrasted settings to also go forward in our understanding of our own stuff, like I discussed for decades with Bob about the mobile meds. But I don't believe that in the area that we're looking at, not so much the top set, but the middle set maybe. And we don't have so much of these, but maybe I'm overstating that. Maybe it's not true, or maybe it's something that we should better look at. So by cross exchanges along our PET delta, that would be interesting. We can gain knowledge on the understanding on how it really works. So that was long.
Great point.
I do think Christoph, if you're burying reduced material, like if you're burying sulfur to any degree, that definitely would change the ballgame in terms of how you would interpret any mismatch between oxygen and CO2. But in the system I'm talking about, there's basically no reduced sulfur that's permanent. I mean, you generate it sort of temporarily, but then it gets reoxidized. So, but I agree with you. That would be certainly an explanation.
I had a question. We're done the last train of thought. Okay. Did I jump the gun on someone? Okay.
No,
This will be quick. It's already been partially answered, I think, by the last round of questions. But my understanding is that there are certain global deltas that are more efficient at burying and sequestering carbon than others. And I'm wondering if there is a dominant mechanism for that. My understanding is that it's mostly just due to barrel rate, but I'm wondering if either, now thinking more about storm systems, if, local climate, wave energy, or even mineral protection could also be playing a dominant role, and what your thoughts are on that.
Well, I have my dominant thoughts on that. And the key to a lot of the carbon burial is oxygen exposure time and integrated oxygen exposure time in the system. And so it may be episodic exposure, but when all is said and done, if the material has seen 100 years of oxygen exposure somehow, that will be a more efficient incineration of the carbon, whatever its source is, than if it has 1 year of exposure total. And so you can think of the different systems and the different particle dynamics and within those different systems that'll give you different outcomes in terms of what is finally buried. And so for example, if material comes into a delta and goes right out into the foreset region and is buried rapidly, that will have a high efficiency of carbon burial and preservation. If, however, it's trapped for physical reasons and in this sort of energetic, highly oxygenated area of the ocean and is cycled over and over and over and over again, then you will get rid of it. So of the carbon. So I think it depends on that transit and residence time of the material in different settings in the system. And that will, as you said, when you started out, will vary depending on the system you're looking at. That's my bias.
I mean, Mississippi River Delta is a classic example. We have such a shallow water depth. We're constantly getting these sediments exposed to oxygen. That's why our organic matter content is 0.5%. I mean, we get so much organic matter, high productivity every year. Where does that carbon go? Goes back to that same classic question, right?
Thanks for your presentations. I think I have one question for Marshall, not Mathiel. Yeah. So I think
we're in that now.
Yeah. So in your talk, I think you mentioned something about like the methanogeneity and the sulfate reduction. And I think if I understand from your talk, you said, very low kind of sulfate reduction, I guess, or.
Well, you can't actually detect it in the sulfate profile because it's reoxidized so fast. So you have to use the radio tracer to actually see that it actually wasn't a very small rate if you compare it to.
Yes. So my really interest is on the couple process between the sulfate and the sulfur and the methane cycle. So exactly in the AOM cycle. I wonder within your study, within your research, whether you guys look into the AOM processes
And also you showed in your talk, although you didn't really show the result, on some models, some reactive transport models that you, so I was wondering what are the outcome from that? Were you able to kind of like piece apart some of the processes that operate within that intermediate cycle between the sulfate and the methane? Yeah.
So we measured methane oxidation with radio tracers as well. And the most intense so far from the data we processed, the most intense zones of methane oxidation are in the surface layer, and they correspond with sulfate reduction. Not in a one-to-one stoichiometry, but there is a correspondence between sulfate reduction and methane oxidation. So we suspect it probably is limited to a very small fraction of the superficial sediment. But what's interesting about that is also then under that, you actually have iron reduction.
Yeah.
So there's like a twisting in the zonation. Yeah. And that is something that we're going to try to elucidate with the reactive transport model that Christoph Mila is currently working on at UGA. So it's a pretty weird situation, I think, when you start throwing the methane in there and seeing how things lay out. So we're digging into it. Great question.
Thanks. We actually need to convene for lunch, but we will have the panel back up at the end of the day and to keep chatting. I'm just going to take this opportunity to ask my question. or leave it food for thought. So all of you have talked about what I've heard from all of you are the difference in kinetics of remineralization, seasonality, what have you. But with respect to remineralization, or even not respect to remineralization, like what Marshall was talking about, you've got different kinetics of formation of different macro and micronutrients. And yet when we're modeling things like the global carbon cycle, perhaps all we're doing is tracking carbon, perhaps. So if we have this decoupling of remineralization that we have seen, for example, the silica cycle, decoupled from organic carbon remineralization. And then we've also seen manganese cycle, iron cycle, different sources of nutrients, not just from rivers or from benthic pelagic coupling. We also have SGD inputs. How do we model that? Because phytoplankton you're not just sucking up CO2. You need a lot of other stuff to make organic matter. So if you could help me answer that question, I would be very grateful.
Yes.